if you have access to Canvas already, raise your hand. Okay, if your hand is not up, you want to talk to me really soon and make sure you have access to Canvas. Okay?
Is the course supposed to be still published?
It should be published.
No, it's not.
It's not published?
Yep.
No.
Ooh. I wonder if anyone is 224 published?
Yeah,
Yes.
24 is.
Okay. Well, let's take care of that. So you've been like waiting in suspense to find out what you're getting into.
Yep.
Publish. Okay. All right, we're live. All right, so Canvas gives you access to basic information like the syllabus and stuff, as well as the homeworks, assignments, access to your grades, and all that kind of stuff. So you want to hop on there as soon as possible. Let me run through the syllabus really quickly and sort of tell you what you're in for, and then we'll start talking about what the course is about. All right, so CSE 215, Discrete Structures. This course lays down, in some sense, the theoretical foundation for what we're going to be doing in 222, which is the winter of the three-course 224, 22, 23 sequence. So it's really good to be taking it right now before 222. If you take it at the same time, it works out pretty well, but taking it before, slightly better. So prerequisite 121, Intro to C, and also Engineering 250. If you haven't taken Engineering 250, you've probably already talked to me. Thank you. About it. We kind of assume a familiarity with things like Boolean logic, basic Boolean operations that we use in a digital design class. But if you haven't already taken 250, it's usually not too hard to sort of pick it up on the way. But let me know if you have concerns about that. So my name's Nick. My office is the opposite side of this wall out here. So if you go all the way down the hall and go in, walk down, find 203J, that's me. My office hours will be Mondays from 4 to 6 and Fridays from 4 to 7, possibly subject to change. But I'll let you know, and they're posted on the door of my office. The textbook is open access, so you can download it from here. You can print it, you can hand it out to strangers on the street, whatever you want. It's all open source. And it's a good text for what we cover in here. I'll let you read the course outcomes on your own. Let's talk about assessment. So, homework questions, 25%. So each week I will give you a series of homework questions. They'll probably be posted on Canvas. And I'll probably give those out on Friday. Or I'll make them available on Friday. With the intent that, that you can work on them over the weekend and ask questions about them at the beginning of the following week. And I'll probably collect them on the following Wednesday. There'll be a number of questions on the homework, but I may only grade one question. I may do more than that, but we'll talk about it. But I won't tell you which question up front. The point being, it's important to do all the homework questions, okay? But I won't necessarily grade every single one. Doing the homework is obviously key to understanding the material. I can stand up here and I can talk and I can lecture, and that's got some value, but the real understanding will come in doing this stuff on your own. So a quarter of your final grade will come from your homework grade. 10% will come from a series of 3 programming assignments, probably all in C. And they're basic assignments, but they let you use some of the concepts we're developing in here in writing some programs. So it's a different way to look at some of the things we'll be talking about. In-class quizzes, 20%. And quizzes will probably be given on Wednesdays. And they may be more than 1 per week, depending on how they go. And that's 20% of your grade. A midterm around end of week 5, 20% of your grade. And then a comprehensive final exam that covers the whole course, that's 25%. And you can look at the course policies, link here to see final grade assignment and other policies and procedures. Hey, how you doing?
Good for you.
Okay. Hey, you get to sign in, because you're actually on the list. Quizzes and exams are going to be closed book, but open note. Okay? Technically, I probably couldn't stop you if you printed out the entire book and said, these are my notes, but I don't want you to do that. Okay? For a couple of reasons. One, I don't want people using laptops or tablets during quizzes and exams. Okay? The real reason is I don't want you to say, hey, I've got this, X 100-page book. I don't need to take notes. All the answers are in here, because they're not. Okay, the answers are going to come out of your head, not out of a text. Not even out of your notes. But in your notes, you can put down the things that help you figure out how to do problems. So this kind of problem, mathematical induction, I have to do these things, I want to remember this, this always trips me up. So I want you to get in the habit of making good notes and working with those notes when you're doing homework questions. Okay, so that by the time you get to a quiz or you get to an exam, you've already got your notes. And you're not spending the night before trying to figure out what to write down in the book on a piece of paper. Okay, so closed book, open notes for the exams. I think that's it for administrative stuff for now. Any questions on any of that? Okay, so let's talk about what we're going to be doing over the next 11 weeks. So we're in a course called Discrete Structures. What could that possibly mean? What does discrete mean? Does it mean we only whisper about this stuff?
Well defined.
Well defined, okay. What else?
Not continuous is what you mentioned.
Not continuous.
That's the one I missed.
So we have discrete and we have continuous. And these are somehow different from each other. Well, what do we mean by continuous?
Uninterrupted.
Uninterrupted. Good. I'll take that.
Beautiful section.
Flowing from one point to another without interruption, perhaps. So suppose I have a point, and I have another point, and I have a meter stick. Okay, here's one now. And I want to know the distance between these. I can measure it, and it looks like it's 59 centimeters. And if I have instead a point right here, it looks like 56 centimeters. And a point right here looks like 64 centimeters. It's actually 64.12173, depending on where I measure it to. But if I'm only looking at the big numbers on my meter stick, 10, 20, 30, 40, 50, and I try to measure the distance from here to here, I'm probably going to say this is 60. And I'm probably going to say this is 60, and this is 60. And this point over here I'm going to say is 70. And as this point moves from here to here, the distance that I call that remains 60. Until I get presumably to where it's actually 65 centimeters. And suddenly it jumps and I'm saying, okay, it's actually 70. And with a meter stick, you're kind of always doing that. This comes down to millimeters. So I could say it's 632 millimeters, or 633, but I probably wouldn't have anything in between there. That's an example of a discrete measurement. Now I could say it's halfway between this line and this line, so it's 632.5. But at some point, even though the distance from here to here changes continuously, I might look at it as a series of discrete measurements. So what does this have to do with being uninterrupted? Think of a number line. And it's a real number line, it's just plain old numbers we always deal with. If I pick any 2 points here, say 0.4 and 0.6, there's a number somewhere in between there. There's a lot of numbers in between, like 0.5. And if I pick this point and this point, there's a number in between those two. And any 2 points that I pick, anywhere on this line, there's always a number in between them. So there's a lot of numbers in between them. That's a continuous distribution of numbers, as opposed to a number line with just integers where there's nothing in between here and here. That's a discrete set of numbers. Discrete because as you move from here to here to here, you have to jump from 0 to 1 to 2 to 3. Whereas if we have real numbers, we move smoothly. 0, 1, 2, 1.3, 1.4, and smaller steps in there and so on. And we'll talk more about this in some detail later on. But this is sort of the heart of what's discrete about discrete structures. We're looking at things that are separated somehow. In engineering CS 120, we build circuits and we use Ohm's law and we use KVL, KCL, and we figure out what the voltage is or the current through some piece of our circuit. And we get a real number as an answer. We get 2.5173. When we get to chapter 5 and we do digital circuits, our answers are always zeros and ones. If our circuit puts out something like 4.73 volts, we just say that's a logic 1. If it puts out something very small, we say that's a logic 0. We discretize our voltages into these two bins, 0 and 1. And computer science, for the most part, is built on digital circuitry, which means we're basically doing discrete math when we do things with digital circuits, with programming languages, and so on. So this will all tie into what we're doing as computer scientists, because computer science is basically digital. Not always. So that's the discrete part. All right, so what are we going to do in this course? This weekly breakdown, subject to change. Okay, we'll start off sticking to it pretty closely, but as we go further, we'll tend to ignore this. What kinds of things are we going to do? Well, we're going to start off talking about set theory. So what is a set? It's a collection of things.
A discrete group of...
Yeah, it's a discrete group. It doesn't have to be discrete. We could have a set of real numbers between 1 and 2. But it is a collection of things. And it could be a collection of numbers. So that's a set. It could be a collection of an infinite number of things. It could be a collection of things that don't seem related to each other. That's a perfectly fine set. It's got 3 elements. It could include things that are themselves collections of other things. This could be the set of all dogs whose breed begins with the letter C. This could be the set of all cheeseburgers that cost less than $2. And so you can have sets of sets, you can have sets that are empty, you can have sets that include empty sets. Just a collection of stuff. And it's unordered, so this collection of things is no different from this collection of things. It's a set that contains the elements 1, 2, and 3. But sets are really, really powerful. Because if we have two sets, say, of real numbers, well, let me use discrete numbers, for example. So here's a set, and here's another set. Let's say that goes on forever. I can define a mapping from this set to this set, which maps each number to what we call its square. And a mapping is just saying I want to associate with each element in this set an element in this set. It's a collection of mappings. That's a set. So I can make a set which says the number 1 is associated with 1, the number 2 is associated with 4, the number 3 is associated with 9. And this set is analogous to what we call squaring an integer. If I gave you this set and I asked you what's the square of 3, you just find an element in here where the first number in this is not a set, this is just an ordered pair, is a 3, and there's the square of it. And I can take arbitrary mathematical functions and I can represent them with sets. And I can take changes of these functions, I can apply functions to other functions, and I can represent that with sets. In some sense, I can take a lot of mathematics, possibly all of mathematics, and just reduce it to sets. It's a really, really powerful concept because it's so simple. It's just a collection of things. So we'll look at how we use sets and how we get from there to functions and sequences and things like that. We'll also discover some perhaps surprising consequences of playing around with sets. For example, we can get into paradoxes. If we take what's this so-called naive view of a set, which is just a collection of things, without being careful what kinds of things we mean, we can get into paradoxes. The famous one being called Russell's paradox. And it leads you to a situation that cannot exist. And it trips you up. It forces you to take a few steps back and say, okay, we've got to change something. We can't just say a set's a collection of things. We've got to be careful about it. Otherwise, we lead into paradoxes. So we'll look at Russell's paradox. And we'll look at the sizes of sets. For example, this is a symbol for the set of all integers. 0, 1, 2, 3, 4, 5, -1, -2, -3. It's all the integers. How many elements are in that set?
Infinite.
It's an infinite number. Here's a set E. It's a set of even integers. How many elements are in that set?
Smaller infinity.
It's an infinite number, but it seems somehow smaller because we're missing half the elements from here. It's still an infinite number, but we seem to be missing half of this, so it should be like infinity divided by 2 or something. And it's not. We can show that this set is exactly the same size as this set in a very formal way. Now this R is the set of all real numbers. That's also an infinite set, but we can show that this is somehow fundamentally bigger than this. It's a bigger version of infinity. So we'll talk about cardinality, which is a fancy way of saying infinities. Looking at the sizes of things where we allow things to be infinite. And we'll say, is there more than one infinite? And the answer is yes, there will be. There's big infinites, there's small infinites, there's really big infinites. But it's very surprising to discover that this and this are exactly the same size. And rational numbers, which are fractions of integers, are exactly the same size as the integers. And the set of integers that end with 100 zeros has the exact same size as this set. And the question of, is there a set with an infinity somewhere in between the size of this and the size of this? That's a question that will ruin your day. That's what's called an undecidable proposition. It's been proven that you can't answer that affirmatively or negatively. It's undecidable. So we'll talk a little about that at the end of chapter 1. And we'll get into all kinds of trouble. This is a course that will touch on some disturbing things, good disturbing things like paradoxes, things that are counterintuitive, limits to what we can do with a computer, limits to what we might be able to do with our minds, things that seem like they should be one way but are very different. And we'll come across these throughout this course. And then we're going to talk about logic, propositional calculus. And if I could name one goal for this course, it might be this. I would like everybody who comes out of this course to have a rock-solid understanding of what constitutes a proof and be able to construct a good, sound proof. And proofs are tricky things, and a lot of people will say, oh, I hate proofs. Because you can't just take what you did for one proof and repeat it for another proof. You got to somehow conceptualize the process of constructing a proof in order to come up with more proofs. But here's a statement. The sun will rise tomorrow. How many people believe that's true?
I'll bet you $50 it will.
Mm-hmm. Which you have nothing to lose. Actually, we might still be around if the sun didn't rise.
That's true. I got that all mixed up. I was misread it as the sun will explode.
Ah.
Will not explode tomorrow.
Right. In which case, that would be a good bet. We believe this. There's really good evidence that this is true. Can we prove this right now, today? It's very difficult, if not impossible, to prove. We can look at what we know about physics and the sun. We can say the sun's not going to explode, the Earth's not going to stop rotating, NASA hasn't reported any asteroids coming in for us, and we can be pretty sure. But to actually prove this, I would say it's probably impossible with what we know right now about the universe, because there could be something that we don't know about. The world is supposed to end on the 27th, by the way. That's the latest date. That's the supermoon. Yeah, supermoon lunar eclipse, and there's going to be a sunset viewing party somewhere here on campus. Dick Schmel, I think, is putting it together. So it's going to be a lunar eclipse and a supermoon, so it should be really, really cool. But that's not until Sunday. So the sun will probably rise tomorrow, but we don't know that for sure. So this is actually pretty hard to prove. How about this? Can we prove 1 + 1 = 2? Do we believe this, first of all? Okay. Can we prove it?
Yes.
How?
If we subtract 1 from 2, we get 1.
Reverse. How do we know that 2 - 1 is 1? Examples. So I can prove 1 marker + 1 marker = 2 markers. And I can prove 1 elephant + 1 elephant = 2 elephants. But how do I know 1 laptop + 1 laptop = 2 laptops? What if it's a new laptop that hasn't come out yet? It might break this.
I think we're gonna need some basic, some basis to be able to prove something, whatever. Like one idea plus one idea could be just one idea.
Yeah, yeah. So we need to somehow nail down what this means, and what this means, and what this means, and what this means. And talk about what it means to prove this.
If we go back far enough to back when they started doing this originally, and we started counting on our fingers, figure out how many sheep we had.
Yes.
You could say that one sheep is clearly a sheep, and this other sheep is not the same sheep, but it's also another one sheep. And if you have two of those, then you have two. There's your answer. Because you define it as there's a sheep, then there's a sheep, that's one sheep. And then here's two sheep, that's two sheep. We put two one sheeps together, we get two sheeps. So it's a
Perfect.
poor explanation, but
No, that's great.
you can.
And that worked because sheep and our fingers were close enough to each other.
But now, when we delve into more complex, abstract arithmetic, we can't use that same concept.
Right.
Because
We're trying to abstract, and we don't know if we can do that. But in fact, this is true. And this was proven less than 100 years ago. It was proven in the 30s. And it was proven by two mathematicians named Whitehead and Russell. And this is part of their proof. This is page 379 of a 2-volume set called Principia Mathematica. And it all looks like this. I have a copy of it on my hard drive. It all looks like this. It's gibberish. But down here, on page 379, they have proposition 54.43, blah, 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 blah. And then they prove it, a demonstration. And then there's a little note here. From this proposition, it will follow when addition has been defined that 1 plus 1 equals 2. So they actually proved this. But that was in the 1930s, and it took a lot of work. So some things that we believe are true, we can't prove. Some things that we believe are true can be proven, but they're very difficult. But we're not going to worry about those too much. Can we prove that?
No.
It's probably not even true. A lot of dogs like bacon. Watch Ultimate Dog Tease on YouTube. CJ, an animal I live with, is a dog. Well, maybe we could prove this if we understood genetically what the definition of a dog was and we did some tests on CJ. But I actually think he's more pony than dog. He eats apples and stuff like that. He prances around. So I don't even know if he's a dog or not. Again, I don't know if that's true or not. I've never given him bacon. Bacon has disappeared when I've turned my back. But CJ lives with his mom, Mango, and Mango always has a guilty look on her face. So I don't know if CJ likes bacon or not. So these three statements, probably impossible to prove if they're even true, but they may not even be true. So we can't prove those, but let me show you something that we can prove. If all dogs like bacon and CJ is a dog, then CJ likes bacon. This we will be able to prove. That's what we'll do with propositional calculus. And we won't know whether these individual things are true, but we'll know that if this and this are both true, then this has to be true. That's the kind of proof that we're going to deal with. But that will lead us into a lot of other proofs. All right, who knows what a prime number is? Someone blurt it out.
A number that can be divided only by one in itself.
Perfect, a number that can be divided only by one in itself. So 7 is a prime number, 9 is not because it's divisible by 3. So we're going to talk about number theory, the study of numbers. And a large part of the study of numbers relates to prime numbers. Overall, maybe a small part. A large part of what we're going to study about prime numbers relates to prime numbers. And divisibility more generally. What happens when you divide one thing by another? What if it doesn't divide it exactly? What happens when you divide 7 by 2? Well, you get 1 left over. That's modular arithmetic, the study of remainders, basically. Primes and divisibilities. So number theory is probably the most popular branch of mathematics for people who are not mathematicians. Because a lot of the really, really puzzling questions are pretty easy to understand without having an advanced background in mathematics. For example, are there an infinite number of primes?
Yes, I can prove it.
Yes, and you can prove it. And Euclid actually proved it, I believe, a few thousand years ago. And the proof is beautiful. And we'll look at that proof when we get to this material. And it's very elegant. And it's an aha when you see it, right? It's a proof by contradiction. There are primes that occur as consecutive pairs. But does this always happen no matter how large you go, or is there some largest consecutive pair of prime numbers? That's an open question. If you look at it, it kind of looks like if you wait long enough, eventually you'll find another pair, but there's no proof one way or the other.
If there's an infinite number of primes, shouldn't there be an infinite number of second pairs?
There could be a point where if you go beyond some number, you never find 2 consecutive odd numbers that are prime. That doesn't mean there's not an infinite number of them. It could just be you always have to add.
Oh, consecutive odd numbers.
Consecutive odd numbers.
Is that it?
I thought that wasn't always the case.
It's not always the case. For example, 7 and 9, that's not a prime number. But if we keep looking at primes, eventually we find another pair. 11 and 13 is another pair. So the question is, do you ever run out of these pairs of consecutive prime numbers? Don't have an answer. It's an open question. Really easy question to state, very complex to try to solve, to try to prove one way or another. And there's a lot of questions like that. The most famous one, perhaps, trying to solve this with integers, pretty easy, 3, 4, 5. That's just a Pythagorean triangle. Trying to solve this with integers, other than 0, 1, 0, very difficult. And in fact, it's been known for a few hundred years that there's no way to solve this with integers, positive integers. But what about x to the 4th, y to the 4th, z to the 4th? X to the 5th, y to the 5th, z to the 5th, or most generally, this is called Fermat's last theorem. And Fermat claimed that he could prove that you couldn't solve this for n bigger than or equal to 3. But he claimed he didn't have enough space to write down the proof. This was a little footnote on the side of a book. And then he died. And people spent hundreds of years trying to figure out how did he prove this. And a lot of mathematics was developed chasing this proof. And it's pretty much assumed he did not actually prove it. He probably had something that looked like a proof but had some technical errors in it. But in the 90s, somebody finally constructed a proof that this was impossible. And it came out of a field called algebraic geometry. And it's a crazy proof. But a lot of mathematics was developed along the way to getting to this. So we'll talk about number theory, and we'll talk a lot about primes. And primes will take us into cryptography. It's a really cool application of number theoretic concepts. And most cryptography is based on the fact that if you take 2 primes, it's pretty easy to multiply them. If you take the product of 2 primes, it can be very difficult to find the 2 primes that gave you that product. Now, if your number is 77, it's not too hard to just start dividing. But if your number has 1,000 digits, and you have 2 500-digit prime numbers that you multiplied, really hard to find those primes. That's the basis of e-commerce. That's why you can send your credit card to Amazon online and somebody can look at what you're sending but not get your credit card out of it. Because they need to be able to factor large numbers into primes. That's why people get excited about things like DNA computing or quantum computing, because those potentially give us a mechanism for factoring large numbers. If you can do that, cryptography fails. So we'll talk about all that. Induction. And this will be maybe the most unpleasant, just based on past responses from people, the most unpleasant section of the course, but it's the most important in some ways. Because induction lays down the basis for everything that we do in data structures. It's the basis for recursion, and we do recursive algorithms when we develop data structures in 222 next term. What's the idea of induction? What's this equal to? We already went over this. Good. Right? Seeing a pattern? If I write this down for n ones added together, I believe I'm going to get n. Can you prove it?
Yeah,
Just don't know how.
in the left side, we should be able to. If you have the left side as a fact, you should be able to prove that from two.
How? You're right.
Couldn't you bust down some compares of 1 plus 1 into like 2, and then use that to kind of shorten?
Yeah, here's the trick. If I can prove this, then I know this is true, because I can add 1 to this side, that gives me n ones. I can add 1 to this side, that gives me n. So if I know this, I can prove this. But I don't know this yet. But if I know this, if I know this, I can prove this. And then once I prove this, I can prove this. But how do I know this?
Somewhere n gonna be equal to.
Eventually I'll get down to this. And I know this because I can pop it into my calculator. And then I can work backwards. That's mathematical induction. And it's a way to formalize this proof process. But we use it all the time without even knowing what it's called. When we write programs in computer science, a lot of times what we do is we solve a problem for a particular case. We're trying to sort a set of numbers. And we say, okay, I think if I do this and I swap these and I move through and I do that n times, I'll get a bubble sort. And we usually work through it in our heads for a small case, and we see that that works. And we convince ourselves that because it works for that small case, it'll work for bigger cases. This is a way to make that rigorous. And once you understand mathematical induction, you're already using it, but once you understand what it is that you're using, it gives you a more powerful tool for doing this kind of reasoning. And it also lets you identify the fallacies where you thought that you could go from here to here, but you can't. And this will tie into recursion, which is a really powerful way to write programs, to implement algorithms. And recursion trips a lot of people up, but once you master it, it's a wonderful tool. It becomes second nature to think about. So recursion we'll touch on in here, but we'll do a lot of it in CSE 222 in winter. And then we'll spend a couple of weeks counting. So yeah, we have a unit on counting. And we'll talk about the following. Here's a box with 6 holes in it. And we have 6 pigeons who are going to take temporary residence in these holes. And it's possible, if we have 6 pigeons and 6 holes, that we could have 1 pigeon per hole. what you want because they don't want to share. Now, it's possible that all 6 pigeons might crowd into this hole, but it's possible with only 6 pigeons and 6 holes that we could have no more than 1 pigeon per hole. But if we have 7 pigeons, that's impossible. The only way we can get 7 pigeons into 6 holes is if at least one of these holes has at least 2 pigeons in it. And that's called the pigeonhole principle. And it's a really kind of obvious but very powerful concept that we can use to prove all kinds of things that have nothing to do with pigeons. Number theoretic results and computer science-y results. And that'll take us into permutations and combinations, probability, Pascal's triangle, all kinds of things related to if you're ordering 5 pizzas and they have 7 toppings available and each pizza has 3 toppings, how many different orders can you make? Good stuff like that. And that'll take us about to the midterm, and in the second half of the course we'll start talking about things that are a little more obviously computer sciencey. So Boolean algebra, a lot of what we did in 250, Boolean expressions, truth tables, sums of products, products of sums, and so on and so forth. That'll mostly be review for people. Graphs and trees will be things that we'll use heavily in CSE 222 data structures, ways to organize information, ways to take problems in the real world like communication problems on a phone system and address them mathematically by turning them into structures like graphs. We'll talk about algorithms in some generality, focusing largely on an analysis of algorithms. How can we look at an algorithm and know if it's correct? How can we look at an algorithm and know how much time it's going to take to execute? And in particular, how much will that time change as the size of our problem changes? If we can sort 100 numbers in a minute, how long will it take to sort 1,000,000 numbers? Will it take 2 minutes? Will it take 1,000 minutes? So we'll look at the growth and complexity of algorithms. And then we'll probably end with automata theory, which is basically a study of computation. Theories of computation, theories of languages. If anybody's familiar with Alan Turing or saw The Imitation Game last year, we'll talk about Turing machines. State machines, which we've done in 250, or you will do in 250. Ways to take languages and identify what's a correct sentence in this language, what's an incorrect sentence. Diagramming sentences, if you've ever done that. Things like that. Huge application to computer science. And then week 11 will probably be just sort of wrap up and review. We may talk about relations, which is a way of looking at functions in set theoretic terms and so on. So we're covering a lot of different stuff. Stuff that may seem unrelated, but the underlying themes will hopefully tie them together. And like I say, these underpin a lot of what we do in computer science. So it's in some sense a mishmash of topics, but it's really not. It's really all kind of related. And it's about 1 subject per week. So it goes pretty quickly. And we'll do set theory for a week, and then we'll jump into proofs. And we won't really be doing set theory when we talk about proofs, even though it's there. We'll be talking about proofs. So it moves quickly, and it's really important to stay up with the material as we go through it, because if you miss it this week, we're doing something totally different next week. All right, any questions, comments, concerns?
So we should start reading chapter 1?
Yes.
I mean, like, yeah, what?
Yeah, go through the book. I don't know if it's chapter 1, but look at the stuff on set theory. But we'll start talking about set theory tomorrow.
Okay.
And we'll go from there. All right, cool. See you tomorrow. My battery died.
If it dies, will it still save?
Hey, it didn't die. It's about to die.